Everyone. So since it's 10 a.m., I think we're going to start right now. Welcome to the American School in Japan's 4th Annual Space Conference. My name is Selena Drysdale, and I'm a senior and a leader of the Space Club. I'm here today with my fellow Space Club leaders, Spencer, Juan, Roshan, and Michio. Thank you for taking the time to join us today. Our mission as a space club is to spread the love of space science throughout the ASIJ community and beyond. So it means so much that you're here online with us today, making this event possible. After Dr. DiBraccio's presentation, there will be a live Q&A session. If you have any questions during the presentation, please type them into the Q&A chat box below. The conference is being recorded as well, so if you'd like to watch it again later on demand, it will be uploaded to our website soon after. Our speaker today is Dr. Gina DiBraccio. Dr. DiBraccio is a research astrophysicist currently at the NASA Goddard Space Flight Center's Solar System Exploration Division in the Planetary Magnetospheres Laboratory as an associate lab chief. She has researched almost every planet in our solar system and is now working on the MAVEN mission, which aims to research the Martian upper atmosphere and ionosphere history. So take it away, Dr. DiBraccio.
Great. Thank you so much for that introduction, Selena. I am going to share my screen so that everybody can see the presentation that I've prepared for you today. And does that look good?
Yeah.
Yep, that looks great.
Great. Okay. Thank you. All right, so today I'm going to talk to you about exploring magnetic fields in space. And what I decided to do was actually split this talk into two. The first part, I want to talk to you about my career, my education, how I got to the job that I'm at. And then in the second part, I want to talk to you about the research that I'm doing and some of the work that I'm doing right now that Selena alluded to in the introduction that she gave me. So before I actually talk to you about becoming a NASA space physicist and how I got there, I actually want to draw your attention to the photo that I'm showing you on the back of this slide. So this photo of the Northern Lights, or the aurora, was actually taken by one of my colleagues. And I was there when this photo was taken because I was in the Arctic Circle in Finland attending a science conference. So one thing that I want to point out is that as a scientist, when it's not in the middle of a pandemic, we actually travel to some really cool places to meet with other scientists and learn about physics, but also communicate our science. So in particular, when this picture was taken, we were attending a meeting where we were talking about the physics of the aurora, and we just happened to be able to see it as well in the Arctic Circle. So that's kind of a little bonus to being a scientist, is that we travel the world internationally to meet with each other because, as we know right now in this virtual environment, these meetings work when we need them to, but sometimes, you know, nothing can be replaced by just sitting down with our scientific colleagues and talking about science or some of the new ideas. And so when I got into science, I didn't realize that travel would be such a big part of the job, but it's just, you know, an added perk. And I've been to a lot of fun places, but the emphasis there is because scientific communication is really important. So we go to these meetings, we give science talks, we write papers, and we learn how to communicate the technical aspect of our science. And seeing the aurora is just an added benefit there. Okay, so when I speak with students, I usually like to, you know, look around and poll the audience and ask a few questions just to gauge the audience and understand who it is I'm talking to. And of course, that's more challenging in this environment as well, but I still want to pose a few questions for you. So let me put them up here. The two questions that I have for you to think about is, what do you want to be when you grow up? And so that first question is probably something that you've thought of, you know, ever since you were little, and you might still be asking yourself that question, especially when some of you are thinking about college and the next steps, you know, in your life once you graduate high school. And for me, you should know that this is a question that I still ask myself because I'm always learning, I'm always evolving, and frankly, I would say I'm not even halfway through my career yet. And so I can go in a lot of different directions. So I still consider asking myself the question of, what do I want to be when I grow up? And then the next question that I want you to think about is, what path should you take to get there? And I really want to emphasize that there's no right or wrong answer. There's no textbook definition of how to get to one specific job or point. But there are different ways that you can get there through work experience and education. And so hopefully, by me telling you the path that I took to become a NASA space scientist, it's just one example of a way to get there. Just know that there are many different ways to get to various careers and jobs. So let's talk about that for me. My education, I went to the University of Pittsburgh for college, located in Pittsburgh, Pennsylvania, and I got my bachelor's degree in physics and astronomy. And then I also got a second bachelor's degree in business administration. So Pitt had this really nice program where I was able to do this dual major with the business school and add that on to the science background that I was getting. And at the time, I don't think I actually realized how useful this business degree would be added on to being a scientist, essentially because when I'm a scientist, I'm responsible for accruing funding so that I can actually do the science that I want. So there's actually financials involved, there's budgeting too, because I need to make sure that I have enough funding to support the other scientists that I'm working with if we're working on projects together. And you should know that not many scientists do have the business degree, but it was an added aspect here that I really benefited from. So that was my undergrad degree. And after I graduated from the University of Pittsburgh, I went to the University of Michigan, and that is where I got my master's degree in atmospheric and space sciences. And then I went on to get my PhD in space science. So I spent 5 years living in Ann Arbor, Michigan, as I got my education at the University of Michigan. So I mentioned education and then I mentioned work experience. I'd like to highlight some of the hands-on work experience that I was able to get throughout my career prior to starting the job that I have now. And I want to emphasize the fact that I think this work experience is by far the thing that helped me the most to navigate the path in my career and where I've actually landed up, because it's taught me what I liked, but more importantly, it's also taught me what I don't like to do. And so I really encourage you, aside from your education, try to get as much different work experience as you can. If you're applying for internships or different programs, test out different things, because you'll quickly find what you prefer and what you don't. So for me, I started with an internship at the NASA Glenn Research Center that's located in Cleveland, Ohio. And I started there for a summer when I was an undergrad. And I was working in a group which eventually they hired me on as a co-op student. So as a co-op student, I was actually switching in between school and work. So what I would do is I would spend one semester at school and then I'd go and work for one semester. Now, during my time at NASA Glenn, I was working more on the engineering side, where we were looking at radioisotope engines for deep space missions. Think about sending spacecraft to the outer stretches of our solar system. So that's what these engines were for. And I learned a lot, and it was a really good experience. But I also learned that I didn't see myself as an engineer working on this aspect. I realized that I really wanted to get into the science more. And so what I did was I took that co-op agreement that I had, the cooperative agreement, and I was able to move to the NASA Goddard Space Flight Center that's located in Greenbelt, Maryland. And one thing that I should point out is there are many NASA centers across the US, and each of them have different fortes and different things that they're known for and that they work on. And so at NASA Goddard, they emphasized more of the science that I was really interested in. So when I moved my co-op there, I got involved in science, and it was something that I realized that I really enjoyed. And so the internships and the co-ops went on through undergrad and into graduate school for me. But once I finished the co-ops, once I finished grad school at the University of Michigan, I went on as a postdoctoral fellow at NASA Goddard. The difference between the postdoctoral fellowship and what I was doing for my co-op is that I actually worked in two different groups. So although I was still at NASA Goddard, I was in two different completely groups, learning different things, working with different people. And the NASA centers are so large themselves that you can do various things while staying at the center for your entire career if you'd like. And so that led me to what I do today. The postdoctoral fellowship that I had, I really enjoyed, and I enjoyed it so much that I decided that I wanted to stay in that group. And lucky for me, they wanted me to stay as well. And so eventually I was hired as a space physicist in the group at NASA. And you can see here in the picture that I'm showing you, this is me giving a talk to some of our important guests that we had on center. I was giving a hyperwall presentation. So we have this really huge screen that shows beautiful graphics. And as you can see, the picture that I'm talking to, that's actually the surface of Mars, a picture taken by the Curiosity rover there. And so in my current job at NASA, I work in the Solar System Exploration Division. And prior to that, I had worked in the Heliophysics Division. So the science that I do actually straddles some of the different science divisions at NASA Goddard. And so from there, I'd like to kind of close out the career aspect and move on into the science. But before I do that, one thing that I want to emphasize to you is that it's really important to have fun along the way. So with this, I kind of want to show you slightly a personal side where, it's not just working, right? This is me growing in life too, as I'm going through these different steps. And so I had a lot of fun with friends and family. So if we just start from the left, if you can see my cursor over here on the left, this is myself with one of my good friends, Dan. So Dan and I went to grad school together, and he also works at NASA Goddard doing slightly different stuff than I do. As you can see, we were in the lab, and that's because he builds instruments in the lab. So in this particular picture, he took me into the lab and showed me some instruments that he was building to monitor charged particles in space. The next picture, you can see that's me and one of my sons. We were just sporting some matching NASA gear on a snowy day and having fun with that. In the next picture over here, if you can see my cursor, that is my sister and I as we were preparing for the solar eclipse that came across the US just a few years ago. So we went to Nashville, Tennessee, so that we could see the total solar eclipse, and we had our glasses ready so that we could look at the sun during that event, and that was a lot of fun too. Continuing over to the right, here I am holding a magnetometer, which I'll explain to you in just a little bit what that is, but I'm holding a piece of hardware that will fly in space one day. So that's always fun, of course, to say that you touched that essentially. And then over here down in the bottom right corner is me at a conference actually in Japan in 2019. So I was able to travel to Japan several times for different meetings. And for this particular one, this meeting, we were talking about the outer planets. So Jupiter, Saturn, Uranus, and Neptune. And that was a great experience. And again, fun being a scientist. So let's talk about exploring magnetic fields in space. And this is where my research goes. This is kind of what I do on a daily basis as far as science analysis is concerned. The way that we explore magnetic fields in space are by using magnetometer instruments. So magnetometers measure magnetic fields at planets, at the sun, and in interplanetary space as well. So wherever we send these magnetometers, they're able to measure magnetic fields. The group that I actually work in at Goddard builds magnetometers. So we have engineers and scientists in our group. And I think that actually makes it even more fun because we work together, the scientists and the engineers. So the scientists come up with the ideas of the science questions that we want to answer. And if we are approved by NASA, if we get funding to go along and try to answer these questions, we actually build magnetometers, put them on spacecraft, and send them out into space to make these measurements. So our engineers build the hardware themselves. Once they're in space and the data are coming back, it's up to scientists like myself to help calibrate the data to make sure that that data can actually be used for scientific analysis. But then after that, it's also my job to analyze it if it's something that I'm interested in doing, and I get to make all the discoveries, with the data that's been sent back. So the picture that you see over here on the left are magnetometers that my group has built for various missions that are flying in space or being prepared to fly in space. So the one that I'm circling with my cursor here, that is a magnetometer that is flying around Earth, measuring the Earth's magnetic field. MAVEN's magnetometer, circling that right here in the center, that is currently flying at Mars, orbiting the planet. Parker is part of a mission, Parker Solar Probe, it's called, and it's exploring the sun. And so we're measuring the sun's magnetic fields with this magnetometer. And then finally, the little one in the front, GTOSat, that mission is a CubeSat. And so we miniaturized our magnetometer so that it's really small and can meet the size constraints and the weight constraints of the CubeSat world. And so we'll be able to measure magnetic fields in space towards different science goals with GTOSat. On the right here, you see one of our engineers that's working in the lab on our instrumentation. So I was talking to you about the fact that I explore magnetic fields in space with the magnetometer measurement, and specifically I work on planetary magnetospheres. So this nice graphic, this video that you see here is demonstrating how a planetary magnetosphere is formed. So we have the sun on the left and the solar wind, which is charged particles flowing off the sun, moving from the left to the right. The Earth has this global magnetic field that essentially shields the planet from the solar wind and radiation that's coming from the sun. And so it forms this cavity that we call the magnetosphere, planetary magnetosphere. Now, in the case of Earth, the magnetosphere covers the entire planet. And because the magnetic field is generated within the planet, we call it an intrinsic magnetosphere. So throughout my research, I aim to look at different planetary magnetospheres throughout the solar system, and I like to compare and contrast them because I use the planets as my own laboratory, right? I don't work in the lab, but I use the data from each planet as my lab. So I essentially am turning different knobs by exploring these different planets to see when various aspects change, how does that change the physics? And so the different planetary magnetospheres that I've explored include Mercury, which also has an intrinsic magnetosphere, this global magnetosphere shielding the planet. And I actually wrote my PhD thesis on some physics of Mercury's magnetosphere using data from the MESSENGER mission. I'm currently involved in some studies at Jupiter as well, looking at Jupiter's magnetic field using data from the Juno mission, which is currently orbiting Jupiter as we speak. And if you haven't done this yet, I really encourage you to look at some of the images of Jupiter that Juno has taken because they are just beautiful. So do that on your free time. For Saturn, I have been involved in projects that look at Saturn's magnetic fields using the Cassini data when Cassini was orbiting Saturn. And more recently, I had been working on Uranus and also Neptune and their giant magnetospheres as well. The story about Uranus and Neptune is fun because the data that I analyzed was actually collected in the 1980s. So it was collected over 30 years ago when the Voyager 2 spacecraft flew by these planets. However, there's still so much more that we have to learn that by revisiting the magnetic field data, I was able to find some new discoveries with it. And so right here, I'm showing you some of the global intrinsic magnetospheres in our own solar system, but I want to shift gears a little bit and talk to you about magnetic fields at Mars because they are unlike anything in our solar system. So instead of these global magnetic fields that I've been talking about, Mars has something that's called crustal magnetic fields. And these crustal magnetic fields you can think of as patches or pockets of fields that are locked into the surface and they rotate around with the planet. Now, we think that Mars used to have a global magnetic field and that it turned off over time. And because it turned off, we believe that these crustal magnetic fields are actually a fossil of the magnetic field that once existed. So they're locked into the surface. And that actually changes the way that the sun and the solar wind interacts with the planet. So if you look at this painting, this watercolor painting that I'm showing you, not only is it beautiful, but it also does a nice job of demonstrating the induced magnetosphere of Mars. So instead of calling it an intrinsic magnetosphere, Mars and also Venus have induced magnetospheres. And so the sun and the sun's magnetic field will interact with Mars, and you see these kind of lumps, they look like these red blobs that I'm circling. Those are the crustal fields, and they just jut out into the solar wind, and they change the way that the sun can interact with the atmosphere of Mars. If you look over here on the right, what I'm showing you is actually data that has been collected by a spacecraft orbiting Mars. And the blue arrows that you see are the vectors of the magnetic field. And you can tell how they're just swirling and spiraling as the spacecraft was orbiting the planet. And so what happened here is the spacecraft was passing through some of the strongest crustal fields located on Mars. And we got to see how the field changed in strength and direction as we flew through. So that's actual data that you see plotted there with those arrows and those vectors. So the way that we are currently exploring Mars is through NASA's MAVEN mission. And I'm working on MAVEN as the project scientist. And MAVEN has been orbiting Mars since 2014. So my group at Goddard actually built the magnetometers that are on board the MAVEN spacecraft. So we provided those magnetometers. And if you look at the picture that I'm showing you on the right here, this is a picture of the MAVEN spacecraft in the clean room before it launched. And so MAVEN has these really long solar arrays that stretch out to either side, and the magnetometers are located on the very end of the solar arrays here. So we put one on each side, and you can think of them as little hands on the spacecraft essentially. And the reason why we put them on the very outskirts of the spacecraft is because the spacecraft itself will generate magnetic fields. And of course, we're only interested in measuring the magnetic fields in space. So we're trying to get as far away from the body of the spacecraft as possible, so that we can understand that we're only measuring the fields at Mars or the fields near the sun. And so speaking of Mars, though, I do just want to pause before we continue talking about my work on MAVEN to also highlight that it's a very active time at Mars right now. This week, there were 2 different missions that arrived at Mars, the Emirates Mars mission, and also from China, they sent another mission into orbit, which will also land on the surface of Mars. And coming up this week, NASA's Perseverance rover will also arrive at Mars. And so it's Mars season right now because there's a very special launch window that makes it optimal to have spacecraft arrive at Mars. And so all of these missions launched at a very certain time so that they could have a very short cruise phase to get to Mars, and they're all arriving at a very similar time too. So I believe it's the 18th of February that Perseverance is arriving at Mars, if you would like to watch that. So continuing on with MAVEN though, MAVEN is exploring atmospheric escape at Mars. We know that Mars was once a warm and a wet world, but the water is gone. The atmosphere is a lot thinner than it used to be. And so current day Mars is dry and cold. And so we're trying to determine where the water and the atmosphere went. So we're understanding how Mars has lost its atmosphere over time by using MAVEN data to explore that. And in this little video that you see on the right here, the colorful particles that you see streaming away from the planet are actually model results where we're predicting where the atmosphere is able to escape from Mars. And so we see that if the solar wind's flowing here from the left to the right, particles are going away from the planet in this area that we call the magnetotail. But you also see this big streak of particles going up. We call that the ion plume, but our nickname for it is also the mohawk of Mars. So these are different ways that we're finding the atmosphere is escaping from Mars. Now, my particular research is looking at the magnetic structure of the Martian magnetosphere. And this is important because the structure of the magnetic fields actually affect how the atmosphere escapes to space. So prior to MAVEN, our understanding of the induced magnetosphere of Mars is just what I'm circling here. We thought that the sun's magnetic field draped around the planet interacted with the upper atmosphere and the crustal fields and formed this simple picture of the induced magnetosphere. However, what MAVEN results have revealed with our magnetic field measurements is that it's actually a much more complex structure than we once understood. So all of the different color field lines, magnetic field lines that you see here are because they're of different origins. So the yellow field lines are field lines coming from the sun. The red have one end attached to Mars and the other streaming out behind the planet out into the solar wind. And these are called open field lines, which allow atmospheric particles to escape. It serves as like a channel for the particles to leave the planet. And then the blue field lines have both fields or both ends attached to the surface of the planet. And you can think of those as the crustal fields that I was talking about. So with MAVEN, we're finding out that this magnetic structure at Mars is much more complex than we thought. And for that reason, it's affecting how the atmosphere escapes to space. And of course, with MAVEN, another thing that we're able to do is understand how changes in the sun will impact that atmospheric escape to space. So when there are solar events, whether they're solar flares or coronal mass ejections, they actually send a lot of energy and radiation towards Mars, and this will increase the rate that the atmosphere is escaping to. And so that kind of gives you a little sense of the research that I'm able to do, some of the missions that I've worked on, and stuff that I do at NASA. And with that, I just want to wrap up with those two questions that I asked you at the beginning of the talk about what do you want to be when you grow up and what path you should take to get there. And so I've explained my path to you. I've given you a little sample of the work that I do, and that's just one example of many. And so, as I said, there's not one direct path, but that's what I did. And trial and error by some of my work experience led me to a place where I really enjoy the work that I'm doing. So with that, I would like to say thank you.
Thank you, Dr. DiBraccio. That was an awesome presentation. So now we'll have our short Q&A session. This is an opportunity for you to ask Dr. DiBraccio any questions you have about her career or the work that she's doing. So if you haven't already, please put your questions in the Q&A chat box now. I'll start out by asking a couple questions that were actually pre-submitted. I'll ask this first one with combining this one with one of the questions that were submitted. So, do you want to go to space? If space travel will soon become more accessible, even for civilian tourists, would you want to travel to the places that you've been studying? If so, is there a certain planet or location that you would want to study more? And if not, why wouldn't you want to go?
That's a great question. So I started when I was really young, and when I would ask myself, what do I want to be when I grow up? My answer was an astronaut, and that is what I wanted to do for the longest time. And I have to admit, I'm a little more hesitant now as I get older and I study space, and that's the honest truth, mostly because things have changed in my life. Frankly, I've become a mother, and I don't necessarily see myself traveling to space until my children are older, for instance. However, I also think it would be pretty cool to go to another planet. If I had to go somewhere, I would love to be on Mars. But as I mentioned as well, I did my PhD thesis on Mercury. And so if I could go to Mercury, I would, just because it would be a lot of fun. However, Mercury is very hot on the side that faces the sun and very cold on the side that does not face the sun because it rotates extremely slowly. So we do not have the technology that would enable us to go to Mercury yet. Another thing that makes me hesitate, though, as far as space travel is concerned, is the amount of radiation that is out there in space. And so astronauts are limited to how much time they can spend in space because of that. And so I would like technology to go a little bit further as far as protecting astronauts from radiation before I signed up for that.
Thank you. So I'm going to ask another question. What is the basic science of how a magnetometer measures a magnetic field? Sorry. Yeah.
No, that's a great question. So simply put, we're using currents where we have a wire that is wound around another wire, and we're able to sense the magnetic field behind it by driving currents through these wires. And so the basic structure of the magnetometer is not too complicated. Because it's just Ampere's law. Use it if you're familiar with that, using the currents and the magnetic field. And if you want to know more about the specific types of magnetometers that I work with, they're called flux gate magnetometers because we're gating the magnetic flux. So if you look up a flux gate magnetometer, they're actually pretty widespread. They're even used on Earth, on the surface of Earth as well. And so you can find some nice documentation to read about the physics behind that in more detail.
This question's another one about more of your career life. And so was this job the original idea of what you wanted, or is this idea of being an astrophysicist something that you decide you wanted to do later on?
It was definitely something that I decided later on. I knew that I was always interested in space and planets, but I didn't really know what the options were as far as working in the field is concerned. And so it wasn't until grad school that became clearer to me, and that was thanks to my advisors that I had. My advisors asked me questions that kind of narrowed or directed the path that I wanted to go on. But frankly, when I started grad school, I didn't even know what a planetary magnetosphere was because I had taken astronomy, but nothing, as far as magnetic fields around planets are concerned. So it was something that I definitely navigated through my education and my career. And one story that I always like to tell is when I started grad school and my advisor and I were scoping out the projects that I would work on, he asked me if I wanted to do data analysis, if I wanted to be a modeler, or if I wanted to work on theories and derive theories. And I answered yes to all of those because frankly, I didn't, at that point, I just didn't know. I wanted to try them out a little bit. And I don't like to say no and cross something off the list unless I've tried it and kind of gotten that experience. And so a little bit of trial and error there. And then I realized that it was the data analysis that I liked. So it wasn't a clear path for me the whole time. I knew what I was interested in. And then I took some experiences, decided what I didn't like, decided what I did. And I kind of took this random walk until I ended up here.
Awesome. Are the crustal fields on Mars fixed or changing? You mentioned they're like fossils of the magnetic field.
Yep. So for the most part, you can consider them fixed. There's actually, I didn't show it on my slides, but we have a nice map of the surface of Mars, and then we can actually show where the crustal fields are located. So we have a good sense of exactly where they are and what their strength is because we've been able to measure these magnetic fields. They do change in the sense that when as I said, they rotate with the planet. So when they're on the side of the planet, the day side we call it, that's facing the sun, when they're interacting with the solar wind, that can actually press on the crustal fields and squish them a little bit. So it will change them with the pressure. But for the most part, they're pretty much static as they are.
This is a question about Mars and its atmosphere, but why do you think Mars lost its atmosphere, and is there a way for it to get it back?
That's a great question. So we think that Mars lost its atmosphere because the solar wind is able to interact with it directly. And so one thing that we did determine from MAVEN is that most of the atmosphere and most of the water on Mars has been lost to space, going out away from the planet. And that's actually really important because prior to MAVEN, we weren't sure if the water in the atmosphere went down into the surface of Mars or if it went out to space. And so with MAVEN, we were able to answer the question of the fact that most of the atmosphere has actually been being stripped away out to space. Now, we think that part of the reason that it's being lost to space is due to the lack of the magnetic field at Mars, that global magnetic field that I was talking about. We think that the magnetic field serves as a shield to protect the atmosphere. However, there are some instances, if you take Earth, for example, although Earth has a global magnetic field, it actually loses its atmosphere as well. However, the atmosphere is a lot thicker than it is at Mars, and it's being lost at a different rate. But there are some studies that show that although Earth has this global magnetic field, the surface area of the global magnetic field can actually channel the solar wind into the atmosphere just at different places and contribute to this escape. So this is a long-winded way of saying that we actually have yet to definitively decide whether the magnetic field helps or hinders that atmospheric escape from Mars. And so that's something that we're currently exploring. Is there a way to rebuild the atmosphere? There hasn't been a convincing way that anybody has come up with yet. Some of the theories that have been suggested would take millions and billions of years. So nothing that would help in our lifetime for sending astronauts to Mars, unfortunately.
So we have two more questions. This one's from a past Space Club leader. Is research on Martian magnetic fields currently being used to inform applications such as manned missions?
Yeah, absolutely. One thing that we've considered, so I just told you about the fact that these magnetic fields, the crustal magnetic fields at Mars, might protect the atmosphere or not. And so one thing that we've explored is considering if we want to send astronauts to the surface of Mars and we want to protect them from the solar radiation, would it be helpful to have them land under one of these magnetic fields? Would it kind of serve as an umbrella to shield them from particles coming from the sun? That's one of the reasons why we also want to understand if atmospheric escape is helped or hurt by these crustal fields being there, because if it shields the astronauts, that would be great. But if it actually turns into, if we have it wrong and it's a funnel where it actually is sending all of these particles to the surface, then that would not be so great, right? And so understanding how these magnetic fields operate on the surface of Mars is really important, because we could use that as a tool to help protect our astronauts if we understand it properly.
Thank you. So this is our last question.
Okay.
What are some possible ways high schools can structure science and engineering programs to make your career field more inviting to different kinds of people?
Oh, that's such a good question to end on. Oh my gosh. Yes. Well, first of all, let me say that when I started at NASA, when I started with my internships and my co-op and whatnot, though that was, I'd say, in the early 2000s, somewhere around 2007 to 2009. When I started then to where it is now, it has diversified tremendously. I was by far the youngest person. I was the one of the only females, and that's not the case anymore. And we're still working to diversify, obviously. So one thing that we're finding is that it really truly does start when people are young and in school, even at elementary school range, right? And the specific work that I'm doing, as I mentioned, I didn't necessarily know much about it until I was in grad school, really. And I think one thing that we can really do is try to be inviting to a diverse population and bring some of these concepts in earlier. I think one thing that students have a hard time with is, you're sitting in physics class, you're sitting in math class, how does it relate to the big picture, right? And for me, I really got excited when I started taking astronomy in high school. So I think if these classes are available at a younger age to get people involved, that would be great. But also, people like to work in environments where they see others that look like them, have similarities to them. And I think it's just making sure that we keep this diversity up, not just when people are in school, but for the long haul, right? And so we're actively recruiting at NASA to try to diversify the people that are working there, because we're hoping that if students come and they see that, we're diverse, then they would want to be as well. So it's always it's a work in progress for sure, but I have hope that it's going to keep getting better.
Well, thank you everybody for coming to today's event, and thank you again to Dr. DiBraccio for sharing your experiences with us. Your insights into the space industry, exploration, and of course your own experiences have inspired and informed all of us today. Hopefully you can come to ASIJ sometime in the future. Before we wrap it up today, we would like to remind everybody that we have two more speakers presenting on February the 21st and March 1st. So don't forget to sign up for those dates if you're interested. Have a great rest of your day, everybody. And Dr. DiBraccio, have a good night.
Thank you for having me.
Thank you.
Thank you, everyone.
Thank you, everyone. Thank you.